Hey there, it's Shannon Matchick-Myers, and today we'll be looking at a specific example relating to circular motion. So we'll look at a 3,000-pound automobile, and it's negotiating a circular interchange of radius r equals 300 feet at a speed of s equals 30 miles per hour. Assuming the roadway is level, find the force between the tires and the road such that the car stays on the circular path and does not skid. Use the force vector equal to m times the acceleration vector a, where m equals 3,000 divided by 32. And we're going to round our answer to the nearest integer. All right. So here, if you have a road, this is a circular motion type problem. So you've got some kind of road here. See how well I draw this. Here's our road. Remember, I'm a math person, not an artist. And you've got your lines in the road. And then we've got our little car. So let's say the car is coming towards us, and we can treat it like a particle, right? So let's make the car, red, have it be sporty. So you've got some kind of car here. And it's got its little wheels. Again, not an artist. And its windows it'll have a lot of windows, I guess, right? Anyway, that's and here's the grill. That's my really funky looking car. All right, so anyway, it's like this particle, and there's this center you can think of over here, right? If you were thinking of this as part of a circle, right? You'd have some center here, and this car, the tire, right, would be touching the road. So this is like our B from our circular motion problems that we were thinking about. Cool so far? And so you have this, this is like our radius, right? So B is equal to R, but what did we find out? We found out that R was equal to 300 feet. Cool? All right, so now we also know the speed of the car. The speed of the car is 30 miles per hour. So assuming that the roadway is level, we want to find this force between the tires and the road, so the car stays on that circular path, right? And so when we do this, what do we know, right? What do we know? Well, we certainly know that that the speed is equal to the magnitude of the velocity vector at time t. And we also know that that is equal to 30 miles per hour. Cool so far? All right, but we have our radius in feet. So one thing we may want to do is figure out, well, what is 30 miles per hour? Sorry, this is another part of the problem. We'll move this down. Let's get our 30 miles per hour and get that in terms of feet. So we can say $30 miles per 1 hour. And we usually will get this in terms of feet per second, all right, feet per second, because we're going to be dealing with that. That's just the typical units. So we want feet per second. So we want to get rid of miles, and so how many feet are in 1 mile? Good, 5,280 feet per 1 mile. And then how many seconds are in 1 hour? Well, there's 60 minutes in an hour and 60 seconds in a minute. So there are 3,600. Sorry, we need to get the hour out of there, right? And we need, so this would be 3,600 seconds per 1 hour. Cool so far? All right. So now the correct, the units that we wanted to get rid of are gone, right? And so when we go ahead and take a look, we'll have 30 times 5280 divided by 3,600. And that is 44. And specifically, it is 44 feet per second. Groovy? So from this result, we got that our speed is 44 feet per second. I'll write it up here. Groovy? All right. What else are we going to need? It would probably be a good idea to find omega, right? Since we are dealing with a circular interchange, right? And the speed, remember, is in terms of, the speed is also in terms of B times omega, right? So maybe it might be a good idea to find omega. And so we can find omega by doing what? Well, what was the speed? The speed was the magnitude of V at t, and that would be equal to B times omega. But don't we know B, and don't we know the magnitude of V at t? Yeah, we do, right? So that would mean that we'd have 44 feet per second is equal to 300 feet times omega. And so what would the feet, do you see, would divide out? So we would have omega would equal to 44 over 300 radians per second. Cool so far? So now we have our angular velocity. All right. Now, our force will end up being m times our acceleration vector, right? But the force is, we want the magnitude of all of that. That's why we're getting magnitudes, right? Because to get the actual force and not just the force vector, you want the magnitude of your force vector. So what'll happen is you will have our force is equal to m times the magnitude of our acceleration vector. Well, the magnitude of the acceleration vector is also equivalent to b times omega squared. Again, we derived that in our last last video, circular motion 1, right? Well, we know all these things. Our m was given as 3,000 over 32 times, let's see, what was b? 300, and then times 44 over 300, the quantity squared. All right, so we get a result of 600, and that's in foot-pounds. Our result ends up being 605 pounds. The next part of the question is to find the angle at which the roadway should be banked so that no lateral friction is exerted on the tires of the automobile. All right, so in this one, we're going to round to the nearest tenth of a degree. If n is normal to the road, remember we want n to be normal to the road. So let's start with that. Okay, so if n is normal to the road, and if we consider, this normal vector, this vector n, and we were to take a look at it, magnitude of n here, and then we would have the force, or the weight of the car rather, the weight of the car. So you're going to have the weight of the car. I'll put that in the car color, I guess. And the weight of the car was 3,000 pounds. And then our force was 605 pounds, right? So here you end up with this angle theta, right? And we want this to the nearest tenth of a degree. So here, well, what do we have? We know that using the fact that we have a right angle here, right? A right angle here. We know that the tangent of theta would be equal to the side opposite, which is 605. They're both in pounds, so that'll divide out over 3,000. And so if you evaluate, the arctangent of both sides, it's just the inverse tangent, you'll get that theta is equal to the arctan of 605 over 3,000. And when we plug this in to the calculator, make sure you're in degree mode. we'll get 11.4 degrees. So theta is approximately 11.4 degrees. So that's the angle that the road, that's the angle that the roadway should be banked, so that you don't have lateral is on the side, lateral friction on the tires. You want the friction on the tires to be on the flat part, right? So so that is how the road should be banked. All right. So hopefully this helps you understand the question, and I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.